Hi, everybody. Let's get started. So this week is arguably the prettiest pictures of the course week. So we're going to start it off in style with Jupiter. And Jupiter is an awfully pretty planet if you go and look at all the details of what's going on in those clouds. We're also going to cover Wednesday is going to be the moons, the outer moons, which are also a lot of pretty pictures. And Friday's the rings, which I think is probably, some people have probably been waiting for that. So today's plans, we have a lot to discuss in terms of the gas giants and their various atmospheres, what is in those atmospheres, the weather of those atmospheres, wind and weather, why do they have the colors they do? There's all sorts of questions that we can discuss here. So to first start off, we're going to discuss the atmospheric composition for these planets. So here's just a bit of a reminder to start off. So primary atmospheres, we've talked a lot about atmospheres that the planet first had. Then you have the secondary atmosphere, what the atmosphere is like today. What molecule, actually, well, not necessarily a molecule, well, okay, was the main component of the primary atmospheres of the terrestrial planets, like when they first formed? I'm seeing a broad mix. The answer that I'm looking for, so this is the primary atmosphere, hydrogen. That's because hydrogen, helium is the majority of what makes up of everything in our universe, pretty much. So when you first started, we had a hydrogen atmosphere, lost it very quickly. We now have a very different atmosphere, of course. But the point is here, yeah, so if you have a primary atmosphere, 94% hydrogen. If we look at the gas giants, they're actually all still fairly close to that original primary composition. I mean, a little bit less. There's now some other things. But they all had the same primary atmospheres. And unlike us, the gas giants kept that original hydrogen atmosphere that they originally had in the early formation of the solar system. So it's primarily hydrogen, some helium, a little bit of debris left over otherwise. So what these atmospheres look like, if you're looking, so you have the molecular hydrogen makes up this layer here. Then you have metallic hydrogen. Then you have that small rock ice core in the center. As a quick check your understanding, why do you guys think the Jovian planets kept their primary atmospheres? And I'm going to give you guys these choices. There's two correct answers for the record, so choose your favorite. So the answer is they have a large mass, and the second one is that they are very cold. So let's break these up. The first is if you have a large mass, that really increases the escape speed from the planet, right? So you imagine, it takes a certain amount of energy to launch off, certain velocity to launch off the surface of Earth. Imagine you're on a planet like Jupiter that's 100 times the size of the Earth. It's going to take that much more velocity to escape. And that's exactly what we see if you're looking at the Jovian planets. The escape velocities are significantly higher than they are our own planet. So if you look at compared to hydrogen, for example, and its average speed and helium, you will see that it's not many of those molecules are going to be fast enough in order to escape those planets by a large margin. The second are very cold. Molecules that are colder, of course, do not move as fast or as often. So that is also going to keep that gas inside close to that planet. So next thing up, rotation and banding. So banding is, there's bands of clouds on some of the giants. We're going to discuss that. So here's a thought for you guys. How do you think we measure the rotation speed of the giant planets? I mean, they're gas giants, so it's not like on Earth. It's somewhat more straightforward. Okay, so I see a few options again. This one, so there's two options. The first is you can track a single feature on the surface. The second is, you probably weren't going to get this, but you can measure the variation in the radio signal. So if you remember from last week, we discussed Jupiter has a giant radio maser that spins around. You can basically, based off of measuring that maser, know exactly what its rotation speed is to within seconds. That's about 10 hours and a spare number of minutes for that interior core of Jupiter. However, it turns out, you can also track a single feature on the surface, but you run into some problems due to what's called differential rotation. What this means is when you think about the gas giants, different parts of that atmosphere rotate at different speeds. So this is if we're looking, this is data from Jupiter taken by the Cassini spacecraft. What you want to look at is if you're looking at the central bands on Jupiter, They definitely move faster than those bands further north or south toward the poles. So what this ends up meaning is, we can measure the speed at the equator for the gas, and we can also measure it at the poles, and we can measure it at the center. You get a lot of different answers based off of which way you choose. So we tend to go by the core because, well, that's the one that, kind of makes sense and doesn't really vary and confuse everyone. So the way banding works, the reason this exists in the first place is, so I'm sure you guys have all heard before that hot air rises, cool air sinks. And that's basically what is happening here. So we have our hot gas. It is going upward because hot air rises. You have the cool gas. It will cool down the higher and higher it gets from the center of the planet. And it is going to sink. So this is going to keep happening. Hot air, then cool air sinks. And then ultimately what ends up happening is the fast rotation of the planet is going to stretch those convection cells of hot gas that you're going to have. And they're going to stretch over time as they're rotating through that atmosphere. And it's going to stretch around the entire planet. So a way to think of a band of clouds, it's like if you had a cloud and it just kept stretching all the way around Earth, that's effectively what you're seeing when you're talking about those giant bands. So there's two things that kind of contribute to these bands on the Jovian planets. So there's the convection and the rapid rotation. As I said, Jupiter rotates only 10 hours. Saturn's also very fast in its rotation. That's much, much faster than, of course, an Earth day. So you end up having a lot of these different zonal flows, things like that. You can see this here, this plot this is wind speed by latitude on the planet. So you can see it's much, much faster on Jupiter than if you're going to the poles. Very similar to Saturn, the fastest moving gas is at that equator. It's a bit different on Uranus and Neptune. Those are smaller. We'll discuss they have different things going on. And what we also see is that there's lighter bands and darker bands on all the planets. It's just most clear on Jupiter. The light bands are basically the upward flowing or the moist gas, the warm gas, and the dark bands are where that gas has cooled down and is sinking, the cool, dry gas. Cloud formation and color. So, here are Jovian planets, Jupiter, Saturn, Uranus, Neptune. I said those wrong, sorry. Anyway, why do they look different? So we said most of them are made up of hydrogen and helium, but they have a bit of something else going on. So what they also have is trace amounts of methane, and then they have trace amounts of ammonia. And this is really going to come into play for how these clouds form and what they end up, the ultimate color of these planets. So in general, you have frozen ammonia clouds on Jupiter and Saturn, and frozen methane clouds on Uranus and Neptune. And we'll discuss, that's what's giving their color. So how do you make clouds in the first place? Sorry. The other one I wanted to say is the second thing that matters here is the temperature. So Jupiter and Saturn, you'll notice the temperature. 115 Kelvin, 130 Kelvin. That's much warmer than Uranus and Neptune, which are much further out. Those are more about 52 Kelvin. For comparison, 115 Kelvin, that's about the temperature on the poles of Mars. So it's like not balmy. You definitely need a jacket, but it's not freezing cold compared to 50 degrees above absolute zero. Methane gas also freezes at 91 degrees Kelvin. So that's another reason that they're going to have different things going on in their atmospheres. The other thing that really matters is the rotation speed for these planets. It's how much there's going to be mixing of things and how much color you're going to get. What we end up with is, so this is from your textbook. These are the different planets and then the composition for these different planets. So it's a little confusing. There's this yellow line here. So that's showing you temperature. And then you're also seeing on the y-axis here the altitude. So how deep do you have to get into this planet to have a certain temperature and to have certain molecules appear in that system? So because I'm sure everybody remembers chemical formulas off the top of their heads in this course, I'll point out that ammonia is Jupiter and Saturn here. So you could see they are present in these planets, not in Uranus and Neptune. Then ammonium hydrosulfide is another key ingredient that's present. Then we have methane, as I said, is what mainly works in Uranus and Neptune. And finally, we also have hydrogen sulfide. So The reason this is important is basically if you're looking at ammonia, for example, ammonia is present in a much lower layer of the atmosphere than Jupiter. Ammonia is what gives those Jupiter bands that are very, very red their color. And as a result, because that ammonia is further down in Saturn's atmosphere, Saturn, like, ignore the rings, does not actually look as interesting as Jupiter as a planet. And that's why. It's because those ammonia layers are much, much lower. You can't really see them virtually on the planet. So most pictures of Jupiter are actually, you've seen a lot of very pretty images of Jupiter. They're often saturated to make the different atmospheric effects look more realistic, things like that. This is actually the first true color image of Jupiter. So like if you were to fly by Jupiter, this is what you look at. You can look at Jupiter with a small telescope and I can confirm that this is what it looks like. You can actually see the bands even with a amateur astronomer's telescope. You can sometimes see the red spot if it's on the disk and things like that. But this is probably more what you usually see when you think of the planet Jupiter. This is basically a planet or an image that has been enhanced because it includes not just the visual light, but it also includes ultraviolet for Jupiter and the infrared light. So if we look at infrared, for example, infrared is often a really good way to trace heat on a planet. So you can see that the bright white here are those high altitude cloud tops. So that very, very cold material, it's blocking a lot of that infrared light from Jupiter. So that's why you have a white band versus the deep clouds, which are very, very dark. You can also see those aurora that we discussed last week at the north and south poles. And then you also just have some haze that occurs. Jupiter is also a bit famous because it has a lot of storms. I will discuss other gas giants also have storms. But Jupiter is probably the most famous because of this storm called the Great Red Spot. So the Great Red Spot has existed as long as we have had telescopes to look at Jupiter and see that it's there. It's first noticed by Robert Hooke in 1664. So we're going on almost, several hundred years of seeing the Great Red Spot. It's basically a high pressure system that is the size of the planet Earth. And it's been stable for centuries. So sometimes they say it's a hurricane on Jupiter. That's not quite accurate, but it's basically a giant storm that just never seems to end. It'll get bigger, it'll get smaller. Sometimes you think it might almost be dying, but then it'll come back. Is kind of the thing. It's a very volatile, but is always kind of their system as well. Jupiter also has white ovals on it. So these are two examples of white ovals that I can show you, that I found you guys. Here's the Earth for scale on these systems. The white ovals are smaller storms. They can also be stable for decades, not as long as the Great Red Spot. The Great Red Spot is very unique. And then you'll have basically clouds that will form a very long time. Sometimes they can merge, they can break up, but they're basically other storm systems that are pretty strong. The reason we have a lot of really, really cool Jupiter images lately, by the way, for all these atmospherics is thanks to a probe called Juno. And I just want to highlight out Juno because some of these, I think, really honestly look like modern art to me more than they look like, storms on a distant planet. So Juno is a very cool spacecraft. It goes, and so we discussed that Jupiter has its giant magnetosphere with all these particles, things like that. You basically can't have a probe just orbit Jupiter because it would not survive very long term. So what the Juno probe does is it goes on an orbit, takes it way, way out from Jupiter, and then it'll fly by super fast because, Kepler's law, if you're going really close in your orbit, you have to go very fast. So it can go very close, take beautiful detailed images of what's going on in these clouds. So here on the left, we have an image of Juno of the South Pole, enhanced color. It's not actually blue if you look, at the images of Jupiter. But the reason it's enhanced is we want to see all these like storms and cyclones here. They're about 600 kilometers or, 600 miles, 1,000 kilometers in diameter, if you're kind of wondering here in sense of scale. These are two other storms that are a bit enhanced, but still look very, very pretty. So I included them. These bands will also, I'm talking about the size of them on the planet, but they go very deep. They can go, 1,900 miles or 3,000 kilometers in depth. So, that's basically the size of the United States almost. Just in how far deep they go into Jupiter is one thing that we learned from Juno. I don't think we unfortunately have time for this, but there's a very cool NASA video. You can go into the slides later and take a look where they simulate what the lightning looks like when you look at Jupiter. So there's lightning on Jupiter in all these gas clouds. It's very, very cool. One final thing that is kind of cool is in terms of storms and things like that, is Jupiter actually is the only planet that we've seen in great detail that had an impact. In 1994, there was a comet called Shoemaker-Levy 9, was discovered by Shoemaker and Levy, and it was their ninth comet, so that's how it got its name. They discovered it, and they discovered that this comet, first of all, was very flat. It was broken up into a bunch of chunks, 20-something chunks, that had gone on a close encounter to Jupiter before, broke up the comet. As you can see, this is what it looked like, and then it was going to impact Jupiter a year later. So the impacts basically went, bang, 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 many times the amount of power in Hiroshima atom bomb in every single one. And then you ended up having these very, very large scars or storms that were created from those cometary impacts. They lasted for several months. And as you can see in this image, they were more clear. This was taken by the Hubble telescope. It was more clear and prominent than the Great Red Spot when these happened. So there's no other place in this course to talk about how cool it was that we've actually seen something impact Jupiter, but this is the place to say it. We also have storms on Saturn. So Saturn has a great white spot is what it's called, of course, because of the Great Red Spot. It's not the same thing exactly. It's a series of periodic storms that can basically become bright or long enough, large enough to be visible from Earth by telescope. As an example of the great white spot phenomenon when it occurs, so this was imaged by Cassini, which was a visiting probe to Saturn. But in December 2010, this was one of those large storms that formed. It emerged, strong wind speeds started pulling the storm across the entire planet, eventually to the point where it went all the way around the planet, and then it ate its own tail and destroyed itself. So this is kind of an example of how you get a band. On Saturn, it did not last very long, but we have seen this phenomenon many times, and whenever you see it, it starts, it's like, oh, Saturn has a great white spot. I also want to say, so somebody in this class the very first day was excited that Saturn has a hexagon. So this is, if you look at the North Pole, I believe, of Saturn, you see that there's this weird hexagon structure. And this is a GIF showing it over time. And so what creates this, we're fairly certain, is it's very similar to Earth's polar vortex. Has anybody ever heard, like in winter, sometimes it's like, oh my God, the polar vortex is coming down into the United States, things like that. There's basically a pocket of very cold air that the jet stream usually keeps way up in Canada, so it doesn't come down to the United States. But sometimes in winter, the jet stream will dip down a bit, and then you're going to get some extra cold air. This is the equivalent on Saturn. It's basically a hexagon right now because of the current conditions on the planet Saturn. It's not necessarily that it's going to be a hexagon forever or was a hexagon before this or that. It's kind of a bit of an anomaly that looks very, very impressive. So we wanted to show it off here. Storms on Neptune. Uranus, as I said, we don't think has as many storms unless you're in that particular parts of its orbit. Voyager 2, though, did see a dark spot on Neptune. So sometimes you'll hear this as the Great Dark Spot. Astronomers are very creative in our names. It's moved and changed sizes. So this was taken by Voyager 2 in 1989 when it visited. But we can see it with the Hubble telescope. It's moved and changed since then. We can also see methane cirrus clouds on Neptune. And yeah, this is, you could see the surface of Neptune can change over many, many years if you're looking at it with something like the Hubble telescope. I'll also remind you, this is not actually the true color of the planet Neptune. Neptune actually is a much, much more drab color we were discussing last week. It's more greenish with a hint of blue, but we have it look like this so you can actually see those surface features on the planet. As a final thing, before we get to the activity, I did just want to show this very cool video I found. So this is from the Juno spacecraft flying by Jupiter. So they took a bunch of images, they stitched them together, some artist conception, to go from one image to the other. But if you were to fly by Jupiter and look at the atmosphere of the planet, this is what it would look like. So There was music on this video, but oh well. So we can go in, you can start seeing there's some lightning features that we're seeing as we're approaching the planet, as I said, from that very, very far out part of the orbit. And as you go closer, so this is going in from the poles, so that's why you have those complicated structures toward the North Poles, those cyclones. And yeah, as I said, doesn't this look more like modern art than something that you'd expect to see in space? That's really always my reaction here. And just one little bit more. So this is the part of the orbit where Juno is going very, very fast because of Kepler's laws. So it's going to swing by this side very, very quickly as it's going to then start leaving the vicinity of Jupiter on the opposite side of the planet. So you're going to see those more red parts near the equator, those ammonium clouds, and a lot of white storms and things like that. So yeah, I know everybody always likes Saturn because of the rings. But if Saturn didn't have rings, I think Jupiter would probably win as the prettiest of the planets. So for very different reasons, but still very cool.